All right, so this class is mostly review of grade 11. We've learned intermolecular forces in grade 11 already, and we're just gonna learn them again, maybe in a little bit more details, and then later we're gonna talk about the different kinds of solid crystals and their different properties. Okay, so we're going to talk about intermolecular forces. Okay, now before we go there, it's important to make the distinction between intramolecular force and intermolecular force. Intra refers to within, okay, and inter means between. So if you have an intramolecular force, that will be the force within a molecule. So the covalent bond will be an intramolecular force, whereas two molecules, the force between the two molecules will be intermolecular force. And intra is a lot stronger than inter, okay, because it takes a lot more energy to break a molecule than to separate two separate molecules. All right, so also a van der Waals force. A van der Waals force is named after a Dutch scientist, van der Waals. This refers to the different kinds of intermolecular forces, okay? And we're going to learn three types of intermolecular forces. We're going to learn about the dipole-dipole force, the London dispersion force, and hydrogen bonding. Now, why are they significant? Because the different forces between different particles, they affect the melting and the boiling point of various substances. If you want to melt a solid into a liquid, you have to somehow break apart their bond with each other. You have to separate the molecules. So the stronger their attraction with each other, the more energy is required to separate them. All right, so increasing a melting point refers to the increase in the intermolecular forces. And similarly, if you want to boil a liquid into a gas, you have to separate them. And the stronger the force of attraction with each other, the harder it is to separate them into the gas state. So the intermolecular forces are the cause of the different boiling and melting points. All right, does that make sense? Stronger force requires more energy, thus higher temperature to pull the molecules apart. All right, so before we get to ranking boiling points, let's actually learn what these forces are and how they came into existence. Why do we have them in the first place?
Mr. Joe,
Yes.
Ty's computer ran out of battery. He's in the waiting room, he says.
You're in the waiting room? Wait, what? Oh, Sai's in the waiting room. Okay.
Yeah. His computer ran out of battery.
Oh, okay. All right, so you have the first one that we're going to look at. You have dipole-dipole force. What is a dipole-dipole force? It is the attraction between two dipoles. That's why you have a dipole-dipole force. How do you have a dipole? Well, you only have dipoles if you are a polar molecule. Okay, if you're non-polar, you have a net dipole of 0, you wouldn't have this force. But if you're polar, for example, in the pictures below, HCl and HBr, both of these guys are polar molecules. So the chlorine is a little bit more negative than the hydrogen. So delta negative on the chlorine and hydrogen is delta positive. And that is a force of attraction. Okay, positive and negatives attract. So as a result, HCl is attracted to each other. Okay, so that is the dipole-dipole force. Now, this attraction is weak because these dipoles are weak. Okay, dipoles are partial charges. They're not fully 1 plus or 1 minus. It is partial. It's part of a charge, but still. All right, it's still a charge nevertheless. Okay, it is better than nothing. So these are weak forces, but these dipoles are permanent. Once you have a dipole, it's always going to be there. It will never disappear because The dipole comes from the difference in the electronegativities of the two atoms. Electronegativity is an inherent quality of an atom. It will not change. So if you have a dipole, you will always have that dipole unless you change the structure of the molecule. So this is a permanent force. Okay, weak but permanent. The next type of intermolecular force is hydrogen bonding. Now, what is hydrogen bonding? Well, this one is a little bit difficult to understand. It is a special version of the dipole-dipole force. All right? It is when you have a hydrogen atom bonded to something really, really electronegative, and specifically oxygen, nitrogen, and fluorine. Only those three. Okay? If you have a hydrogen bonded to any of those three atoms, well, the hydrogen will be bullied by those atoms, and the electrons will be really attracted to those three atoms, and hydrogen will be really positive, and those three atoms will be especially negative. So you have an especially strong dipole in this case. All right, and this will attract another electronegative atom. So that hydrogen, the special hydrogen bonded to a really negative atom, will be very positive. And because you're very positive, you're going to attract a very negative atom, like another oxygen, nitrogen, or fluorine. And this attraction is strong. Okay, it's way stronger than a normal dipole-dipole. So this is a special type of dipole-dipole. This is the strongest type of intermolecular force. So if you examine the three pictures below, you can have this exist between hydrogen and fluorine, HF. F is the most electronegative atom at 4.0. Okay, so when hydrogen is bonded to F, you have an especially strong dipole, and that hydrogen will be especially attracted to another fluorine. So that's a strong force of attraction. Same thing with the alcohol. When you have ethanol, that means you have hydrogen bonded to one oxygen, and oxygen is the second most electronegative atom on the periodic table. That means the hydrogen bonded to that oxygen will be very positive, and it will be attracted to another oxygen very strongly. Okay, same story with water, which is why water has a really high boiling point, because it's really difficult to separate water. Which brings us to the properties of water. Because water is capable of doing this hydrogen bonding, and water is special in that it can do 2 hydrogen bonds per water because it has 2 hydrogens, this makes it especially strong. This gives the high boiling point property of water. It takes 100 degrees to boil water, whereas it only takes negative something to boil other gases. Okay, so that's why water has this really, really extremely high boiling point. Also, water has a viscosity. Okay, you have water droplets. Why do you have a droplet? Shouldn't gravity flatten the water on the surface of the earth? No, because the surface tension of the water molecules like to hold on to each other. So the force of attraction between the water molecules overcome the force of gravity, so they don't fall flat, they coagulate in a little droplet. Okay, that's why you have water drops. And lastly, ice floats on water. That is extremely weird. A solid should sink in a liquid because solids should be more dense than liquids. But water is the exact opposite. In fact, this is so common that you don't really think that this is weird. You go get ice water, you go to McDonald's, you get Coke, you put some ice, it floats. You don't really second guess that. Oh, okay, ice floats. You learned that from a young age. But if you learn chemistry, you realize water is, well, I want to say the only substance because I can't think of anything else. So water is the only substance that has this property. All other substances, the solids, will sink in the liquids. But because of hydrogen bonding in the water, the liquid water actually is closer together than solid water. If you have ice, you have a crystal structure formed via hydrogen bonding. Okay, the waters will hydrogen bond with each other, and they will form a hexagonal structure that is quite rigid. But as a result, they kind of spread out because there are holes in them in the hexagons. So the lower density of ice allows it to float. Okay, so that's hydrogen bonding. The next force, and the last force that we're going to look at, will be the London dispersion force. All right, so what is the London dispersion force? Well, this force, first of all, exists in everyone. Okay? This is the only force that exists in non-polar molecules. Because if you're non-polar, you're not going to have a net dipole. So you won't have a dipole-dipole. And similarly, you're not going to have hydrogen bonding because that's another dipole. So the only force that non-polar molecules have will be London forces. Okay? And this is not exclusive to non-polar. This is for everyone. If you are polar, you still have a London force because they come from electrons. As long as you have electrons, you will have London force. Okay, and London force will increase when the number of electrons increase. So the more electrons you have, the stronger the London force. Now, how does that work? Well, London force is due to the temporary attractions between temporary dipoles. What do I mean by a temporary dipole? Check out the picture on the bottom right. That represents two different atoms. Electrons move around randomly in their orbitals. Okay? And let's say on some occasion, by fluke of chance, most of the electrons end up on one side of the atom, which would make that side of the atom slightly more negative than the other side because that side would be deficient of electrons. It would be delta positive. But this is temporary because electrons move around. They will immediately move back. Okay, so for one split moment, one side of the atom is more negative than the other side. And this will cause a temporary attraction on another atom that happens to have electrons on one side as well. All right, so in the picture, those two atoms got lucky to have this configuration, temporary positive, temporary negative. They're like, hey, positive and negative, they attract. But then immediately after, the electrons move back and that attraction is gone. But then later, another one might come up because they move around randomly. And if you move around randomly, this is bound to come up at some time. And because of the sheer number of atoms, a rare event like this becomes common when you have literally like hundreds of trillions of atoms trying to do this at the same time. So you're going to get a lot of this interaction. And obviously, the more electrons you have, the stronger that temporary dipole can be. So this is caused by electrons, which explains why more electrons will have a stronger London force. Now, this exists in all types of particles because everyone has electrons. All right, so basically this is like a you tried ribbon. Like you enter a contest, you sucked, you didn't win anything, the judges give you a ribbon. Well, thank you for coming. All right, everybody has one, nothing to write home about. So everybody has London force. And if you're non-polar, well, that's the best you get. All right. If that's the best you get, well, that is your main intermolecular force. And London force is the weakest of them all. Just based on the description of what I said, that sounds weak. You have a temporary dipole from electric charges that won't be there in the next second. That is just pathetic. Okay, it's still a force. I mean, it's weak, but it's still there, and it adds up if you have enough electrons. But most non-polar substances are gases because they have weak attraction between each other due to the weak London force. All right, so you have a really low boiling point. So do we have any questions regarding London force? All right, so more on temporary dipoles. These dipoles are created from the random movement of electrons, and they will disappear, hence temporary. Okay, this is different from permanent dipoles because permanent dipoles result from electronegativity difference, and that doesn't disappear because electronegativities don't change. Okay, so to repeat what I said, electrons move randomly. There is a chance that it just so happens that most electrons end up on one side. So you have a higher density on one side for just a split second, more negative. and the side missing the electrons more positive. And this gives rise to London force. And London forces keep flips back and forth between the different atoms, but nevertheless, they do make them attract for some reason. All right, so molecules will always attract each other if they don't have a charge. If they do have a charge, then they could repel, depending on the charge. But if they don't, if they're neutral, they will find a reason to attract each other purely because they have electrons and the London force exists. So more electrons, stronger London force. Okay, they add up. So let's compare the different forces that we've learned. So you have hydrogen bonding. This is intermolecular between two different molecules. And you only have hydrogen bonding if you have a hydrogen bonded to NO or F. Okay, it is not enough to have hydrogen and oxygen. They must be bonded together. If you have hydrogen bonded to carbon and that carbon also has an oxygen, that is not hydrogen bonding because the hydrogen is not bonded to the oxygen. Okay, so make sure that the hydrogen is bonded to one of those three. And then there's another molecule that has NO or F, then you have hydrogen bonding. This is the strongest type of intermolecular force because you have the strongest dipoles. The next tier will be dipole-dipole. Also, intermolecular exists between different dipoles. It's just that now you don't have a restriction what that dipole is. Any dipole will do. As long as you're polar, you have dipole-dipole force. Okay, and of course, stronger the dipole, the stronger this force. And then lastly, you have London. London exists in everyone and their grandmas. Okay, this is intermolecular between two different particles, and everything has electrons. Unless you're H plus, then you don't have electrons. But you know, most things are not H plus. So everything has London force. More electrons, stronger force. But this is the weakest of them all because this is temporary. Okay, so these are the three forces. And we can also compare this to the intramolecular force, like covalent bonding. This is due to an overlap of orbitals. This is a sharing of electrons. This is a really strong bond. And then lastly, we have ionic bonding. This is due to the attraction of full ions, full charges. Dipoles are partial charges. They're less than 1. But if you have an ionic bond, you have a full 1 plus, a full 1 minus. That is way stronger than any dipoles you can have. So ionic bonds are also very strong. And you can rank them. Which of the 5 forces do you think is the strongest? Does anyone want to answer that? No ideas?
Covalent.
I'm sorry?
Covalent. It's just a guess.
Covalent. Okay. You're right. Covalent bonds are the strongest of them all, followed by ionic bonds. Okay, covalent bonds are stronger than ionic bonds because covalent bonds have overlapping orbitals. The atoms are simply closer to each other. Now, these two bonds, ionic and covalent, they're a lot stronger than the intermolecular forces. Okay, these two are intra, the other 3 are inter. Imagine it this way. You may have friends, okay? However much you like your friend, you're going to like your arm more. Okay? It's easier to put a wedge between a friend and another person than to cut off their arms, okay? So because intramolecular forces are within the same molecule, it is really difficult to break that apart. But it's relatively easier to break up 2 separate molecules because they're already separate. They're not bonded to each other. They're just attracted. You see the difference here? So intra always stronger than inter. Now within the inter, hydrogen bonding is stronger than the other 2. And then you have dipole-dipole and then London. London is last. Now there's a greater or equal to. The reason for that is London is cumulative. Okay, if you have enough molecules and electrons, the London force can overtake dipole-dipole. In fact, sometimes it can even overtake hydrogen bonding if you have enough electrons. That's the power in numbers. Okay, so now let's use intermolecular force and compare the melting and boiling points of substances. So I have listed 4 things. If you check out nitrogen, all right, the boiling point of nitrogen, the temperature at which nitrogen becomes a gas, is a whopping negative 196 Celsius. We don't have that on Earth. Okay, that temperature does not exist on anywhere on Earth. But we do have liquid nitrogen on Earth. We can arbitrarily make any temperature except absolute zero. We can cool nitrogen down. If you can manage to cool it down to below that temperature, the nitrogen gas will become a liquid. Okay? Oxygen gas can also become a liquid. You can have liquid oxygen. All you need is negative 183 degrees Celsius. Again, we don't have that temperature anywhere on Earth unless we make it in the lab. But notice that oxygen has a higher boiling point than nitrogen. All right, it's easier to get liquid oxygen than liquid nitrogen. Why is that?
Wait, I have a question.
Mm-hmm.
I don't know the answer to your question, but wait, so if it takes more energy to pull molecules apart, which is what you need to do to boil something,
Mm-hmm.
therefore creating more heat, how can the boiling point be that negative if you're making more?
Because their attraction is ridiculously weak. You don't need a lot of energy to pull them apart. You see what I'm saying?
Yeah, okay.
So can anyone explain why oxygen has a higher boiling point than nitrogen? Okay, that may be a difficult question. If you look at NF3, the boiling point is negative 129. So it's still very cold. NF3 is usually a gas. But that is higher than oxygen and nitrogen. So can you explain why NF3 has a higher boiling point than oxygen? That's an easier question. Still no?
Because it got different, like, atoms, or like, yeah. Or
Okay,
like,
they have different atoms. I mean,
I don't know. Okay, there's like intermolecular forces compared to. Oh, okay.
we all have intermolecular forces.
Actually,
You're right, it has to do with their intermolecular forces.
Does nitrogen have a triple bond?
Yes.
And oxygen only has a double bond, right?
Uh-huh.
So it's harder to rip apart a triple bond?
No, you don't rip it apart. You don't rip up nitrogen to boil nitrogen. You just separate them. You see what I mean? If I ask my students to separate step aside, I don't cut you in half.
Well, then on nitrogen, there's only one lone electron pair on each. Well, on each atom. With oxygen, there's 2, so it's easier to pull apart the electron.
Not really. See, you're thinking about their structure because we've been learning structure for the past few days. I think your mind is stuck on that. We're now learning intermolecular forces.
But wouldn't the repulsion between the electron pairs be greater in oxygen and therefore easier to separate because they stay farther apart from each other? Oh, that makes backwards sense, but
not really, no. All right, so think about their intermolecular forces. Nitrogen is non-polar, yes, because it has one element. It's got to be non-polar. You have no electronegativity difference, so the electrons are evenly distributed. So you obviously don't have dipoles. So the only intermolecular force you would have would be London force. And if you count the electrons that nitrogen has, nitrogen has 7. I'm talking about total electrons, not valence. 7, but then you have 2 of them, so you have 7 plus 7, 14. So nitrogen has 14 total electrons. Oxygen, same story, okay? But the nitrogen is non-polar, so the only force is London. Now, count the electrons for oxygen. Atomic number is 8, so you have 8 electrons per oxygen, so 16. Again, you're an element, so you must be non-polar. So the only intermolecular force you have is London force. So they're exactly identical in their intermolecular forces, but oxygen has a higher boiling point. That means it takes more energy to separate oxygen than to separate nitrogen. And the reason has to do with their only difference, the number of electrons. Oxygen has 2 more electrons than nitrogen, so therefore oxygen has stronger London force than nitrogen. Does that make sense? Because London force can come in different strength, depends on how many electrons you have. And because oxygen has more electrons, you have stronger London force. This translates to higher boiling point. Does that make sense? But why is NF3, why does that have a higher boiling point than the other two? Well, it has 34 electrons. But that's not the main reason. So obviously you would have stronger London force, but NF3 is a polar molecule. All right, nitrogen has electronegativity of 3, fluorine has 4. So that's very polar. And if you're polar, your main force will be a dipole-dipole force. Now, notice I wrote main, not only. It also has London force. But when you have both London force and dipole-dipole force, the main force is the dipole-dipole force because that's the stronger force, right? When you apply for a job, you write down your highest diploma because you went through a lot to get there. If you have a PhD, you're gonna put that down. You're not gonna bother say, "Hey, I graduated high school." If that's not your highest diploma, don't bother writing it unless you want to write it for another reason. Like, for example, I will write that I graduated high school on my resume just to tell you that, hey, look, I went to a Canadian high school, so I know what the high school is about, so hire me as a teacher. So that's a special case. But then if you're hiring for any other job, why would they want to know what high school you went to? That makes no sense. They want to see your highest education. Same thing here. You want the strongest intermolecular force. I rate the strongest one, dipole-dipole. So still, it has London, but strongest is dipole-dipole. So dipole-dipole is a stronger force than London force. That's why it takes more energy to separate the molecules between NF3s. Does that make sense? So it has a higher boiling point. Now, water has a ridiculous 100 degrees Celsius. All of these things above have negative boiling point. Most gases do. But water, being a tiny molecule just like the other guys, is special. It has only 10 electrons, so the London force is not the answer here. This is polar. But water can exhibit hydrogen bonding, and hydrogen bonding is a lot stronger than a normal dipole-dipole force. And because of the strength of the hydrogen bond that water has, it has a ridiculously high boiling point. Okay, do we have any questions about how to determine which thing has a higher boiling point?
Mr. Joe?
Yeah?
I just forgot how to calculate the total number of electrons.
Okay, we're talking about total number of electrons, not valence electrons, okay? So an atom would have the same number of electrons as protons. If you're neutral, just look at the atomic number.
Right.
Oxygen has atomic number of 8, hydrogen is 1, but there's 2 of them, so 10 in total.
Okay, thanks.
You're welcome. Okay, so this chart is very interesting. Check out the trends in boiling point down a column on the periodic table. All right, so if you look at that graph in black, you have group 14. So if you just take out a periodic table, check out group 14, you go down the column, you start with carbon. Under carbon, you have silicon, and then you have germanium, and then you would have tin as you go down the list, okay? CH4 has the lowest boiling point. SiH4 has the second highest. And then GeH4 a little bit higher. And SnH4 a little bit higher still. Okay? But they all have low boiling point. They're all below 0 on the graph. Now, does anyone want to explain why? I might ask you to explain why do you see a pattern like this on your test? Okay, does anyone want to take a crack at this? Why do you observe that pattern for group 14? Anyone? Okay, no brave takers. You have to explain two things. One, why is it so low? Why is it all below 0? Two, why does it increase as you go down the column? Okay, first of all, why are they all so low? Why do they have low boiling points? Anybody?
There's not
No?
very many electrons.
Wait, say that again?
Not very many electrons.
Tin has a lot of electrons.
Well, that's at the highest boiling level. But
Yeah, but like, that's still below 0 though.
yeah,
Because they have like the dipole,
I can't hear you.
because like they don't have the hydrogen bonding, but instead they have a dipole force, so they're low.
They don't have hydrogen bonding, you're right, but they don't have dipoles either. So notice methane, CH4, okay, that's natural gas. That's the gas we burn for heat. That is non-polar. It's a tetrahedral. You see what I mean? AX4, that's a tetrahedral. So all the dipoles will cancel, so you're non-polar. In fact, if you notice all of them, because they're in the same column, they're all non-polar. Right? If you go down the column, all of them would have 4 valence electrons, and they would just make 4 bonds. They're all tetrahedrals. So you have all non-polar molecules. And if you're non-polar, the only force you have is London, and that is pathetically weak. Okay, that explains why they have low boiling points. Does that make sense? Natural gas is a gas because it is non-polar. Now, the number of electrons will affect the boiling point ranking between each other. Tin is the highest because it has the greatest number of electrons, because if you go down by another row, you're going to have a lot more electrons because you're bigger. Okay, tin has more electrons than germanium. Germanium's got more than silicon, silicon's got more than carbon. So that's why boiling point increases as you go down the periodic table in the same column. They have the same intermolecular force, all London, but tin has strong London, whereas methane has weak London. That makes sense, right? All right, let's check out the other groups. Wait, what the hell? Why does it not look the same? Wait, look at the water one, group 16, the red line. Water is H2O with oxygen being in row 2. H2S is the row below it, and then selenium is below sulfur. Tellurium is below selenium. So they all have 6 valence electrons, and if you slap on 2 hydrogens for everybody, it makes sense that tellurium, Te with 2 hydrogens, that has the highest boiling point. That should make sense, because tellurium has the greatest number of electrons, right? So strongest London force. That one is higher than selenium. Selenium is higher than sulfur because selenium has more electrons than sulfur, but sulfur has more electrons than oxygen. Wouldn't H2S have a higher boiling point than H2O? But why does H2O shoot all the way up to 100? Why?
Hydrogen bonding.
Yeah, exactly. Water is capable of hydrogen bonding, and despite being a small molecule with very low numbers of electrons, the strong hydrogen bonds will give a high boiling point for water. Okay, the London force no longer matters because hydrogen bonding is so strong. Okay, does that make sense? So that's why you have an anomaly in this pattern. You might expect to find water in that dashed line where that should be if you just extrapolate from the data, but no, because of hydrogen bonding, water shoots up. Okay, if you check out group 15 and 17, the green and the blue, you see the exact same pattern. HF, HCl, HBr, HI. Those are the halogens, the acid for the halogens. Iodine has the highest boiling point because it has the greatest number of electrons, greater than bromine. Bromine has more electrons than chlorine. So you would expect HCl to have a higher boiling point than HF. But no, HF has a really high boiling point. It has a positive boiling point. It's above 0. All right, because of the hydrogen bonding that exists in HF. Same thing with NH3, PH3, ASH3, and SPH3. Ammonia has hydrogen bonding due to the nitrogen. The other guys don't. So that's why you have anomalies. Does that make sense, guys?
I have 2 questions.
Right.
Why are HBr and HI in group 17 why do they have a lower boiling point than group 15 if they have more electrons and all they have is a London force?
Oh, that's a good question. I have no clue.
Okay.
Look it up.
Second question is what makes like hydrogen specifically with nitrogen, oxygen, or fluorine?
Oh, but why those 3 specifically?
Yeah.
Because that's the number 1, number 2, and number 4 on the periodic table in terms of electronegativity.
Okay.
I know what your next question is. What happened to number 3?
No, I was just gonna say so is everything else still hydrogen bonding? It's just
No. Only those 3 we define to be hydrogen bonding.
okay. Why though?
Okay, why? Because they have exceptionally high boiling points. Now, what happened to number 3? Right? Because fluorine's number 1, oxygen is number 2, nitrogen is number 4. No, number 4, yeah. Chlorine is number 3. But chlorine doesn't exhibit hydrogen bonding. And the reason is because chlorine is not in the second row. It's too big. Right? Because you're too big, despite having high electronegativity, it's you're too far from the nucleus, so it's a weaker attraction. That doesn't count. And just empirically, we determined the boiling point of all of these substances, and a pattern emerged in that NO and F has the highest boiling point. And we summarized that, and we concluded that it must have been the strong intermolecular interactions between the dipoles. So we give it a new name, hydrogen bonding. You see what I mean? Anything else? No? All right. Here's a video on intermolecular forces. Wow, there's a lot of messages in the chat. All right, so here's an example where you have to rank the boiling points of various substances. All right, and you have already seen the assignment. There's already a question like that. The way you do this is you just have to figure out their intermolecular forces, which ones are stronger, and then therefore that's how you will rank them. All right, so try to work this out on your own. Try to rank them in increasing boiling points. Now keep in mind that when there is a tie, you need a tiebreaker. And so, for example, if they're both nonpolar, so the only force they have would be London, well, the tiebreaker is who has more electrons, you see what I mean? But if they're both polar, so both of them have dipole-dipole and none of them is hydrogen bonding, what's the tiebreaker? You still consider the amount of electrons. So the London force will be the tiebreaker. So make sure you know that. And then take like, I don't know, a minute or 2 just to finish this example, rank them in increasing boiling points.
Wait, why isn't it the electronegativity is the tiebreaker for polar?
Oh, because the difference between the polarities is kind of insignificant unless you jump to hydrogen bonding. So actually, London force, they add up. So that's cumulative. That's the tiebreaker.
Okay.
Okay, so in order to rank these, you have to determine all of their intermolecular forces. And in order to do that, you have to determine whether it is polar or not. All right, so I'm going to categorize them according to their main intermolecular force. So the only molecule in that list that is capable of hydrogen bonding is the ammonia with the H and the N. Two of those above, aside from the ammonia, they're polar. So HBr and CH3F. The rest of them are non-polar, so they only have London force. So hence, they're like that. And since there are multiple molecules in the same category, I need a tiebreaker. So the number of electrons would be the tiebreaker. So if you have more electrons, you have a higher boiling point within your group. So as a result, the weakest one, you start with the ones that only have London force. Helium has 2 electrons. You're pathetic. You're the first one. And then methane, only 10 electrons. You're next. And then nitrogen with 14, krypton with 36. So once you're done with the London, you go to the next tier, the dipole-dipole force. CH3F, only 18 electrons, you're up next. And then HBr, having 36, you're the second highest. And then finally, hydrogen bonding is number 1, NH3. Okay. Again, keep in mind that this is just a rule of thumb. It could be possible that something with only London forces overtake something with dipole-dipole or hydrogen bonding. For example, if you have gasoline, gasoline is completely non-polar, 8 carbons, 18 hydrogens. It only has London force. But gasoline is a liquid at room temperature, whereas ammonia is a gas at room temperature. So because it has so many electrons, it's got 8 carbons and 18 hydrogen, the London force becomes so strong that it's stronger than the hydrogen bonding of ammonia. So on the test, I wouldn't worry about that. I would just follow the rule because I'm going to choose the ones that don't have this exception. They're all going to be similarly sized. So dipole-dipole will be stronger than London. Hydrogen will be stronger than both of them. Okay, so make sure you know how to do this.
Wait, why wouldn't CH...
Yeah.
Okay, so go ahead.
Oh yeah, sorry about that. CH3F, right?
Yeah.
Why wouldn't that be polar or like have hydrogen bonding?
Oh, why wouldn't that be hydrogen bonding? Okay, I'm glad you asked. Just because something has H and F doesn't make it hydrogen bonding. The H has to be bonded to the F. And none of the H's are bonded to the F. They're all bonded to the carbon. Does that make sense?
But like when bonding to other molecules like that.
Yeah, still, in order for a hydrogen to be eligible for hydrogen bonding, that hydrogen must be bonded to NO or F. Only then that hydrogen will be specially positive. If you bond to a carbon, you're not going to be that positive because carbon doesn't have a high electronegativity. So those hydrogens are just quite normal. So even if you have a really negative atom like fluorine, the hydrogen doesn't really bond to that fluorine really strongly because the hydrogen itself is not that positive. Does that make sense?
Oh, okay. Yeah.
So it has to be bonded to N or F. If you're bonding to any other atoms, and just because you have all of them doesn't mean there's hydrogen bonding. So to be sure, draw the structure and check. Okay, that's a good question. There was another question?
Yeah, for the same molecule, like how do you know it's polar? Can you actually calculate the electronegativity when there is like 3 different?
Yep. So for the same molecule, so let me just draw that. You have carbon with the fluorine and 3 hydrogens. So the electronegativity of hydrogen, I believe, is 2.2. Carbon is 2.6, and fluorine is 4. The electronegativity difference between the carbon and the hydrogen doesn't matter. It's 0.4. It's quite low. But there is a huge difference between carbon and the fluorine. And because this is asymmetric, you satisfy both conditions. You are asymmetric and you have a large difference in electronegativity, which makes you polar. The fluorine will be the delta negative part. The carbon will be the delta positive part. Does that make sense?
Yeah, so basically if you have 3 different elements and you want to calculate the electronegativity, you just subtract all the numbers?
Well, in a way, yes. What you do is you draw the structure and you look for symmetries. Okay? If you have 3 different elements, you're probably not going to be symmetric. Okay, you're not going to be the same in all directions. And then you would just then look at the electronegativity differences between the central atom and the atoms that it's bonded to. In this case, carbon and F, carbon and H. You don't compare between H and F because they're not bonded to each other. You see what I mean?
Mm-hmm.
So any other questions, folks? All right, so let's move on to the last little bit. Different types of solids. Okay, we're going to learn 4 different types of solids: ionic, covalent, metallic, and covalent network. We're going to first summarize each. How do you get these solids in the first place? Well, check out the table on the bottom. If you have an ionic solid, you have an ionic compound, like a metal and a non-metal, okay? If you're a metallic solid, this is something that we've never learned before, you just have a pure metal or an alloy of metals, just metals, none of them are non-metals. A molecular solid would be non-metals bonded to each other via covalent bonds. And then if you have a covalent network, then you have metalloids or non-metals bonded in a special giant network, a web of covalent bonds. And we're going to show you examples and properties of each of these, starting with ionic compounds. So this is grade 10 knowledge. We learned this in grade 10, what an ionic compound is. Basically, that is a crystal lattice structure of alternating ions. Okay, so take sodium chloride, table salt, for example. That is just an alternating crystal lattice of sodium ions and chloride ions. They separate each other, and they make little cubic structures. If you just view sodium chloride crystals under a microscope, you can clearly see that they're kind of cubic, okay? So a crystal lattice is just a crystal of ions. Does that make sense? Some properties of ionic compound, they're all hard and brittle. Hard meaning that you press down, it doesn't really change shape. Brittle means you crack it with a hammer, it breaks. Okay, these two are not exclusive to each other. You can be hard and brittle. Just because they're hard doesn't mean you won't break. It conducts electricity only in aqueous solutions or a liquid. So if you take an ionic solid like sodium chloride, in the solid form, your table salt is not going to be a good conductor. But if you dissolve that in water, all the ions will break apart, then it becomes conductive to electricity. Okay? Or if you have enough heat to melt your sodium chloride into a liquid form, then the ions will be now free flowing. It will still conduct electricity. Okay, so ionic bonds are formed from opposite charges. Now, the boiling points of ionic compounds are really high. It takes around 900 degrees Celsius to melt salt into a liquid. You can't do that in your frying pan. Okay, that temperature is not going to reach 900 degrees Celsius. Pop it in the oven, it still doesn't help. You're not going to melt salt in your kitchen. If you do, it will be molten and it will glow orange. Right, so why does it take so much energy to melt salt? Because you got to break the ionic crystal to do that. And you need a lot of heat in order to break all of those crystals because of the strong ionic bonds. Does that make sense?
But then why does it dissolve in water so easily?
Well, because you have a lot of water molecules, and the bond that forms, the hydrogen bond that forms between the water and the ion, that is also very strong. So you just convert one bond into a different type of bond. So that's easier to do. Whereas breaking them up, you're just literally breaking them without forming new bonds to replace it. Does that make sense? If you dissolve salt, water will surround each sodium and chloride ions so that the negative part of the water will face the positive sodium, and the negative part of the water will face the positive. Wait, I said that twice. You know what I mean, vice versa. All right, so the sodium and the chlorine will be preoccupied with the hydrogen bonds that the water have, the ion-dipole interaction that water gives. They won't try to go back. You see the difference here?
Yeah. Okay, thanks.
All right, so the next part, metallic bonding. What is a metallic bond? How is it possible that a whole bunch of metals all wanting to lose their electrons to make positive ions, how is it that they're together in a metal? And metals are pretty rigid. How? Well, you have a metallic crystal. How this works is, well, the electron C theory will apply. What is the electron C theory? So electron C theory basically says the electrons in those metals become delocalized. Okay, they run away from their atoms and they are now collectively owned by the group. So they're not private properties of that individual atom anymore. It's now a collectivization of all the electrons, and they are free to move around in the metal. So it's as if you have a bunch of protons in a sea of electrons. That is the electron sea theory. So if you collectively own all of the electrons as a group, you are metallic bonding. And this is quite strong. Metals don't break easily. You see what I mean? So some metals are hard, some are soft. So metals, they have many different properties from each other, because different metals have different metallic properties. Some metals are more metallic than other metals. So some metals are hard, like iron will be a hard metal, titanium will be a hard metal, sodium, the alkalis would be soft metals, aluminum is also quite soft. Some of them have really high melting points, such as tungsten, the highest melting point, and then the lowest, mercury. So they have various different properties, but in terms of their metallic properties, their luster, all metals are shiny. Their conductivity, they all conduct electricity. Think about it, they have a sea of free-flowing electrons. Of course they conduct electricity. And they're malleable, you can slam them into thin sheets. They're not brittle. You're not going to shatter metal. You're going to change the shape of the metal instead. Okay? So these are metallic bonds. Does that make sense, guys? All right. The next one is molecular crystals. As you can imagine, molecular crystals are held together by intramolecular forces between molecules. Okay, don't get confused between molecular crystals and molecular covalent networks. They're not the same. A molecular crystal would be a molecule such as iodine, I2. That's a covalent bond between the two i's. Well, iodine, if you look on the periodic table, it says it's a solid. Why is iodine a solid? Well, because iodine is a huge molecule. It has a lot of electrons. The extremely strong London force between the iodines will make it stick together. Okay, so it is held together by London forces, which is relatively weak compared to the other types of forces. So you can melt iodine quite easily. It doesn't take a lot of temperature to melt iodine. All right, so same thing as ice. Ice is H2O. Now, H2O is a molecule. It's held together by covalent bonding. Water, when frozen, forms ice. And an ice is just a crystal of hydrogen bonds. So ice is held together by hydrogen bonds. Hydrogen bonds are strong, yes, but they're not as strong as ionic bonds. So in order to melt salt, you need 900 degrees. But to melt ice, you only need 0 degrees. You see how this works? Because the hydrogen bonding between the water is relatively weak compared to ionic bonding between the salt. So to melt a molecular crystal, you don't break the water. Okay, that's electrolysis. You don't break water molecules, you break water from each other. So molecular crystals therefore have low melting points and they lack hardness. You can easily crack ice. It's not easy to crack an ionic compound. All right, does that make sense, guys? This explains why you can melt sugar in a frying pan. And, people have done that for cooking. Sugar, glucose, well, actually, the table sugar you eat is sucrose, if that's a glucose and a fructose, that is a giant molecule. Okay, the sugar crystals, they are held together by hydrogen bonds between the sugar molecules and the London force between the sugar molecules, both of which are relatively weak compared to the ionic bonds of salt, which is why you cannot melt salt in the kitchen, but you can melt sugar in the kitchen. All right? And these things are terrible conductors because they do not have free-flowing electrons and they do not have ions. You need those to conduct electricity. So these are molecular crystals, okay? And don't get this confused with the next one, covalent network. These are also covalent bonds, but this is a web of covalent bonds. It's an interwoven network. And these substances are extremely hard and they are brittle and they have ridiculous melting points. Okay, they're extremely high in their melting point and they don't conduct electricity because, again, they don't have free-flowing ions. Diamond is the classic example here. Diamond is extremely hard. Now, why is that? Why is it so hard to break diamond? Well, because diamond is a crystal that has a network of carbons. Each carbon is bonded to 4 other carbons in a giant 3-dimensional web. So if you want to scratch carbon, or if you want to scratch a diamond, well, guess what? You have to break all of those covalent bonds in order to do that. It's easy to break one bond. It is not easy to break a million bonds. So that's why they all reinforce each other. And carbon, well, diamonds, they don't usually break. You can still technically break it. Okay, it is brittle. Hard means resistance to scratching. If you have a diamond ring, you're welcome to scratch it against any surface. Nothing's going to happen to your diamond. You will just scratch whatever you're scratching. All right. If you take a sledgehammer and try to break a diamond, if you don't have enough force, you're going to fail. You can smash the diamond with a hammer, and you will probably dent the hammer and the table, but the diamond will stay intact. Doesn't mean you can't break it, though. If you use a hydraulic press, you can still break the diamond. It will shatter into pieces, so it is still brittle. You just need enough force. All right. Quartz will be the other type of covalent network that we're familiar with. Quartz is silicon dioxide. That's the constituent of sand. That is also a network of covalent bonds. It's not just one single element, it's 2. It's silicon and oxygen in a network. Sand also has ridiculously high melting points, okay? So these are really hard to break. See how this is different from molecular crystals? Diamond versus water. Diamond is held together by covalent bonds. Ice is held together by hydrogen bonds. You can easily crack and melt ice, but not diamond. So any questions about that?
Is that what graphene is?
No, graphene is different. Actually, on the next slide, you can see something like that. So what is the hardest thing in the universe? Anyone?
I feel like diamond's the wrong answer.
Yep, diamond is the wrong answer. Diamond is the second hardest thing in the universe. So the hardest thing in the universe is your Unit 1 test. All right, I'm just kidding. So next one. All of these are covalent networks. Okay, diamond is so versatile. It can make covalent bonds in many different creative fashions. Figure A is just diamond. Okay, a carbon with 4 bonds to other carbons. Figure B is graphite. That is your pencil lead. Okay, you write with carbon. And you can see that you have sheets of rings of carbon. Okay, and they will slide off and they're held together by London forces. That's why pencil is able to leave a mark. When you trace with the pencil, you are leaving behind a trail of graphite. The next one is a buckyball, carbon 60. that carbon is making 3 bonds with the other carbons, and you form a soccer ball looking like thing. It's called the Buckminster ball, named after a person. I think his name is Buckminster, so we call it a buckyball. And the last one is carbon nanotube. Again, same idea. It's just instead of a ball, we make a tube. Okay, and there are many applications of these. These are very strong structures because of the covalent network. So we can build tiny nano devices using these structures. Right, so technically you can take pencil lead or any of these and make it into diamond. We can create diamonds in the lab. You just need high temperature and high pressure. It would be the exact same diamond. So I don't know if you watched that TV series. You guys are probably too young for this, but when I was younger, when I was in high school, there was a TV show called Smallville. It's a terrible show, but I had nothing better to do. The internet wasn't that good back then, okay? I had the TV, YouTube wasn't a thing. So I had to watch something, and Smallville was on. And Smallville was about like Superman when he was a kid, when he was in high school and all that. So young Superman. Basically, he wanted to propose to Lana, I think. He didn't have money because he's a reporter, so he wanted a diamond ring. So being Superman, he took some coal. He squeezed them in his hands. The pressure and heat turned it into diamond. And he took a metal ring and smelted it on using laser vision. There, a diamond ring. So that's technically possible if you have enough pressure and heat. So the writers of that show really got creative with the science here. And the last thing we're going to talk about are the semiconductors. They used to be called metalloids. When I was in high school, I learned metalloids. This is a relatively new term. They came up with this. They changed the term recently. So semiconductors are the same as metalloids. They're the half metal, half non-metal staircase that separates the metals and the non-metals. They're mostly used in electronic devices. And what makes them special? Well, metals are great conductors of electricity. But if you raise the temperature, their conductivity will decrease. Okay, if you heat up a metal, it doesn't conduct as well anymore. Opposite is true. If you cool a metal, you will make it better at conducting. So that's how you get superconductors. You cool metal to a really cold temperature. Now, semiconductors work the exact opposite. If you increase the temperature, it becomes a better conductor. So that we call them semiconductors. And your chips, the silicon chips in your phone, in your computer, well, it's called silicon chip for a reason. It's made of silicon, a semiconductor. Okay, germanium, arsenic are also used in chips. So that's all I want to say about semiconductors. This is it for this lesson. Intermolecular forces, very important that you know these, the difference between dipole-dipole, hydrogen bonds, and London force. Why you have them. You have to be able to explain what causes these forces. And also, you have to rank boiling points using these forces. All right? And then finally, differentiate between the different kinds of solid crystals and some of their properties. All right, so do we have any questions before we end it? This will be the last lesson for the entire unit. Anything? All right, good. So I'm going to end the stream right here.